So today we are going to deal with the size of the nucleus. In atomic and molecular physics, we talk about the distances in angstroms. Okay, similarly, when you are dealing with the nuclear and particle physics, the size is in a femtometers. So this femtometer is nothing but a 10 raised to minus 15 meters. Okay, so this is 10 raised to minus 10 meters angstroms. But when we are going to nucleus, okay, so we talk always in a femtometers. So size of the nucleus is in a femtometers, which is 10 raised to minus 15 meters. Now suppose, as I always say, nucleus is not a classical mechanical entity. It's not like a very hard ball. Okay, so we always draw the picture of the nucleus like this. We can draw, but it is never like this. It is not a classical picture. It is not having any classical shape like it is a hard ball. Okay, but it is a quantum mechanical entity, I would like to say. So when you are talking in terms of the waves, you cannot speak about the radius. You cannot say that the radius of the nucleus is like this. So I would like to use the word radial extent. Okay, so radial extent means the shape of the nucleus is somewhat like this. So these are the nucleons which are uniformly distributed up to some distance, and after that they are randomly distributed like this. So for such an entity you cannot speak about the radius. Okay, so nothing is hard boundary is not there. So this quantity is called as a nucleus. Now this up to some distance the charge distribution is uniform, and after that the charge distribution is not uniform. Okay, so we can speak this as a radial extent from this to this. Up to some distance the charge distribution is uniform, and after that the charge distribution is not uniform. Okay, so this has some formula. So we can calculate the radial extent of any nucleus by using formula R is equal to R naught A raised to 1 by 3. So this R naught is called as a shell cap or a nuclear cap, and this R naught is equal to 1.2 femtometers, which has a fixed value. So this R is equal to R naught A raised to 1 by 3, where A is the mass number. So by using this formula, you can calculate the nucleus of any nucleus in a periodic table. Suppose this is a graph of a binding energy per nucleon. So this is like this. So this is a B. This is a mass number. This is a B per nucleon. So on this graph, so some hydrogen and helium are lying over here, then carbon, nitrogen are somewhere here, and this is CO, Ni, Mn, Fe. These materials are lying over here, transition metal ions, and FCO is over here. CO, Ni, Mn, Fe are over here, and some uranium, sodium are somewhere like here. Okay, so by using this formula, if you calculate the radial extent of all these nuclei, you are going to get that in a whole periodic table the range of the nucleus lies in nearly a range of 2 to 8 femtometers. That's it. Okay, so if you try to calculate the size of the any nucleus, then it will lie somewhere about from 2 to 2.8.6, somewhere is there. Okay, so if you try to calculate the radial extent of say suppose carbon, so we know that the carbon has a mass number of the 12, so R is equal to, So this 1.2 femtometer will be fixed, and then 12 raised to 1 by 3. So if you have the lighter elements, I will like to call these as a lighter element. These are the medium weight elements, and these are the heavy weight elements. Okay. So when you go to the lighter nuclei, so they will range in the they will have the radial extent in the range of the 2 femtometers. If you go for the middle weight, they will have the radial extent of nearly 4 femtometers, 4 to 6 femtometers, and above that the radial extent will be somewhere from 6 to 8 femtometers. So the radial extent of all the nuclei in a periodic table ranges only from 2 to 8.6 femtometers. You can take many examples and you can do the homework by using this simple formula: R is equal to R naught A raised to 1 by 3. Now this, why this R naught is fixed over here? Suppose if I take the carbon, the so this is the imaginary, say, picture of the carbon nuclei. Okay, so this shell cap is 1.2 femtometers, and this shell cap remains constant. Now if I go for the, suppose this is a carbon, if I go for this iron, so this uniform charge distribution, so this will increase, but yes, the shell cap remains 1.2 femtometers only. So this 1.2 femtometers remains constant, and this is a uniform charge distribution. So the inner nuclear size will go on increasing, but the shell cap remains constant. The size of the shell cap remains constant. If I go for a uranium, so again the inner core, or the uniform charge distribution in the inner core, that size will increase, but still the shell cap will remain constant for that. So this is how the nuclei in an all periodic table look like. So as I always say, this is not a classical picture, this is an imaginary picture, because when you are going to deal with the nuclear and particle physics, so this is all quantum mechanics. So inner core, the uniform charge distribution of the uranium, this is greater, but the shell cap still remains 1.2 femtometer. So this quantity we have fixed over here, which is called as the shell cap or the nuclear cap, and which is 1.2 femtometers. And this is the uniform charge distribution, which goes on increasing from the lightweight nuclei to the medium weight nuclei to the heavyweight nuclei. Thus, by using this a simple formula of R is equal to R naught A raised to 1 by 3, where A is the mass number and R naught has a fixed value of 1.2 femtometers, you can calculate the radial extent of all the nuclei in the periodic table, starting from the lower weight nuclei to the high weight nuclei.